Thank you very much for the invitation. It's a very big pleasure for me to be here. And I'm gonna be a very good speaker. So let me a moment to make, so wait. This one. How can I, this one. Okay. So my talk about the very great problem in group theory and modern algebra, of course. This is the Kaplansky zero divisor conjecture. This is a very well-known conjecture, and unfortunately, there are no some method how to attack it. And in my talk, I will talk about some very interesting approach, very interesting way. This approach belongs to Roman Mikhailov from St. Petersburg. This approach has a homological and homotopical spirit, and I'm gonna try to be, how to say, okay, I understand that homology and homotopy algebra, this is a very abstract algebra, and I have to use some special words how to describe some constructions, and I hope that it will be very nice. So let's see. But first of all, let's recall the historical background of this problem. And what is this? So we have a group G. We have a group G, and assume that this group has a torsion. For example, some Gn equal to 1. Of course, we assume that n is greater than 1, and n, of course, must be finite. And let us consider the group ring. I think it will be better if I recall what does it mean group ring. So this is a definition. So if we have a group and if we have some ring, of course, we assume that this ring must be associative and commutative. So the group ring is the ring of these formal elements. This is, of course, finite sum, we assume. And finite formal sums and with multiplications, which is defined as follows. So this, of course, this means, of course, multiplication in group sense in our group G. Well, okay, let us return to our presentation. So we have a group with a torsion. And if we consider now the group ring, we, of course, get this equality. It is very easy to verify it. Yes, instead of z, instead of integers numbers, of course, you can consider any field, any ring. This is not a big problem. The problem is still complicated, so don't worry. Okay, we see that we have zero divisors, non-trivial zero divisors in our group ring if G is a torsion-free. Okay, and assume now that G is a torsion-free group, and Kaplansky zero divisor conjecture states that the group ring does not contain non-trivial zero divisors. That is, it's a domain. As I told, it's never mind if you consider instead of a ring of integers number, any field or any other ring. The problem is still complicated. And again, there is no other ways how to solve it. So this is the Kaplansky zero divisor conjecture. This conjecture was born in 1950s years, something like this, and maybe I think maybe more, maybe older. Okay, and what is the progress? We have some progress. Maltsev in 1948 and Newman in 1949, independently of them, they proved that if G is ordered group, then conjecture is true. What does it mean? Ordered group. This is a definition. So we say that group is said to be an ordered group if any element of G are linearly ordered with respect to some relation, of course, total order. That is, for any ABC, if we have A less than B, that it must imply that CA must be less than CB and AC must be less than BC. So for these groups, for this kind of groups, ordered groups, this conjecture is true. Let me give some examples of ordered groups. In my opinion, the very important example, this is braid groups, pure braid groups, and however, pure braid group is really ordered, by the braid group is just left orderable. Well, left orderable means you consider this definition, but without left here, yes, without this one. So left ordered, this one implies only this, only this. However, braid group is for braid group, this conjecture is also true. Let us recall what does it mean braid group. I think this will it will be very nice. Braid group, geometrically, I think it will be better to use this language. Geometrically, any braid group in n strands, you see, one etc n strands is generated by these guys, sigma and sigma I inverse, where this is, we have a crossing, overlapping and underlapping, overcrossing and undercrossing. So this is a generator, and they satisfy some very nice conditions, which are very important in quantum physics, some Younger-Baxter equality and so on. You see, it is, I think everybody see that this is true as this one and this one, yes. And any braid, of course, we can picture like as follows, something like this. You see, we have some braid, and we can decompose it as follows by using our by these generators. The generators called Artin generators in honor of Emil Artin. Okay, so this group is left orderable, but Kaplansky zero divisor problem is true for this group. Pure braid group, it is a subgroup, normal subgroup in wait a moment. In how to kill it? Wait a moment. This one. Pure braid group can be, any element of pure braid group can be presented as follows. We have an order 1, 2, 3, and so on. In this case, 1, 2, 3. We have 3 strands, but any strand which is start in some number must be end in other number. Sorry, this is not pure braid group. I'm so sorry. Okay, so I told the definition that any strand must be a start in some number and end in the same number. I'm sorry, this is not pure braid group. Okay, so for pure braid group, it is also true. It is also well known that any pure braid group, it is a semi-direct product of some copies of semi-direct product of free groups, some orders. Okay, another group. This is the very famous.
And how can one order such braid groups?
Oh, this is complicated. It's called Dernois order in a honor of Patrick Dernois, and it is complicated to say it. I think if you wish, we can talk it later. But it is okay. It is complicated. Okay. Yes. It is not so trivial. Okay, another kind of groups. This is Thomson group F. We have 3 kind of Thomson groups: V, T, and F. I think again it will be better if we consider the definition. Moment, what's happened? I know what's happened. So I use Wikipedia. What does mean Thomson group? This is definition of Thomson group of kind F. It can be presented as follows: just 2 generators and just 2 relations among them. So this is Thomson group. This group is very important for algebraic topology, for another kinds of mathematics. And this group also have some very interesting mysteries and so on. But it is not so important for us. This is just an example that for Thomson groups, this conjecture is also true. Okay. You can see this is the links in archive. If you wish, you can. If you wish, this is the references. Well, another kinds of groups where Kaplansky's conjecture is true is the supersolvable groups. It was proven by Farmanek in this year. I want to pay your attention in the time distance between this result, yes, you see 1948, and this result 1973, yes. This is the next step, that any supersoluble group, for these kinds of group, this conjecture is also true. So this is a definition of a supersoluble group. That means that it has an invariant normal series where all factors are cyclic groups. So this is the definition. You can see that means if you, as well known, denote that normal subgroup, yes, and or any of these every this guy must be cyclic. So for this group, this conjecture is also true. What else? Okay, polycyclic bifinite groups.
Sorry, returning to this supersoluble. What is the difference with usual definition of solvability? Just that each next group is normal in the whole group G, right?
Exactly, and this must be a subgroup in the previous one also, and this guy must be cyclic, any factor, any quotient.
But this condition you can achieve for any solvable group that such factors are cyclic. What is important maybe that this HI is normal in a whole group G, right?
Yes, yes, I'm sorry, yes, you see, each HI is a normal in G, yes, this is the difference.
At least for finite group, you can always achieve that this is cyclic. Okay.
Yes, okay, and another kind of group, the last one where the conjecture is true is called polycyclic bifinite groups. So this definition is a little complicated and was proved by Kenneth Brown in this year and Farkas and Snyder in 1976, again independently of them. And but it is very essential to say that field K must be a field of characteristic 0. I mean, for our group ring, but now we have a vector space, of course. Oh, sorry, algebra. So it is very, very important that field must has a characteristic 0. This is a definition of polycyclic group. Yes, this is a definition. So first of all, this is a solvable group with cyclic factors. You see that G is polycyclic if and only if we have a chain subgroup. So this is definition of polycyclic group. And then we say a polycyclic bifinite group is a group having a normal subgroup H of finite index, which is polycyclic. So this is a definition of this very interesting kind of group. And as I told, these guys, they prove this conjecture if field is field of characteristic 0, but in generally, this conjecture is still open. You see, for this case, it is also a problem. It is also open question. Is it true or not? But I don't know how to attack it.
I'm sorry. And now I have the same question. What is the difference between polycyclic and solvable groups?
I'm sorry, if we have a polycyclic group, yes, and what the difference between polycyclic group and supersoluble?
No, supersoluble is differ from solvable because every GI is normal in G. But here this condition omitted, so it seems that this is just definition of solvable group.
Sergey, here we consider infinite group. Now I understood, because the conjecture is trivial for finite group. In finite group, we always have torsion. So here we consider infinite group. And for infinite group, solvability means that these factors are abelian. And here you ask these factors to be cyclic.
Okay, and for infinite group, no, there is no way replace abelian factors for cyclic factors.
Yes, okay. No way.
I'm sorry.
We can consider, I think we can consider only finitely generated groups, and abelian finitely generated is very close to cyclic. And I think the reason is that the factors are not always abelian. Or no, or we should have always abelian. factors.
No.
For solvable groups, such factors are abelian.
Mhm. Yes, and here we just require that this is a cyclic.
And the question is, if we have an abelian finitely generated group, then it is just a sum of cyclic summands.
Maybe it's useful to note that a subgroup of finitely generated group need not be finitely generated.
Okay, maybe this is a problem. Okay, it seems that
Yes, yes, thank you very much for your question. And there is this also result that if G is torsion-free abelian group and R is integer domain, so this conjecture is also true, but it is not so easy to see that this is true. Okay, so can I continue or not? Maybe you have some other questions. Okay, continue, yes. So for the torsion-free abelian groups, this is conjecture is also true. And I'm sorry, for the last, this is the last kind of group where this conjecture was proved, where group is a unique product groups. This was proven by Cohen in this year. The definition is follows, that group G is called a unique product group if for all empty finite subsets, this is not necessarily subgroups, this is just subsets, there exists an element G which can be uniquely written as a product. So this is very important. And it is not
very
so
strange definition, very strange. So just one element for all pairs of finite subsets, there is just one element which can be written uniquely.
Not necessarily one. Exists an element.
Mm-hmm. So
not necessarily
our
one.
requirement concerns only one element, but for each pair of subsets.
Yes, for each pair, for each subset, you can find some element G, yes, and you can, it's just uniquely written as a product.
Okay.
Aware the strange, I don't know.
Somehow emotionally, so I don't see reason for such a condition.
I see.
Excuse me, am I right that in this case the proof is easy or not? So I think every element of group.
Yes, you are perfectly right. It is not so hard. It is not so hard. Yes, you can of course use your mind and some ideas, but it is really not so big problem. You see, this is for example, this is the first step how to prove it. First of all, it is not so hard to see that only torsion-free groups can be up groups. Up means unique product. You see that it is very easily follows from the definition. You can see here, and it was a very big hope in these years that what if all torsion-free groups went in unique product groups? That means that Kaplansky problem will be solved. But Promislov found in this year examples of torsion-free group without the unique product property. It was published in this year, 1988, and this is very nice result. You can see here, this is the link. So this group is not unique product group, but torsion-free. And so that means that Kaplansky problem is still open. However, this group, yes?
Sorry, Viktor, now I see. This unnatural definition comes from an attempt to prove the conjecture, right? So this definition was produced somehow artificially, just to get a simple proof of the conjecture, and then try to prove that all torsion-free groups have this property, right?
I think you're right. Unfortunately, I don't know this question clearly, but it seems, yes, it seems you're right, yes.
But maybe this property is quite natural to think about when you think about this conjecture, because when you have a product of two elements, you can decompose it every element into sum of group elements, and then you want their products to satisfy some relations, and then if there are some pair of elements which have a unique product, and and this product cannot be received as the product of any two other elements, then the conjecture is automatically true. But that's
yes, I think you are right, and I think also have some ideas about this, because we had 3 Kaplansky problems, and we will talk about this. And we have a dependent conjecture. This is the big one. And from a dependent conjecture follows zero divisor conjecture. And it can be proved by using the fact that group ring is prime. That means that if product of ideals is 0, that means one of these ideals must be 0. And this is, I think it's closer to this definition in some sense, of course, technically, but maybe you are right. I am not a big expert in this question of this historical background. I'm sorry. And okay. So I continue. These groups, actually this group is well known for specialists in algebraic topology. It is a torsion-free, but no right orbital, first of all. And this is extension of abelian group and Klein-4 group. This is the Klein-4 group. This is a definition, just to remind what does it mean. And this is a simplest example of group with these properties. So this was a historical background. And as I told, there are another 2 related conjectures, Kaplansky idempotent conjecture and unit conjecture. Idempotent conjecture is follows, that is for a field K, this guy does not contain any non-trivial idempotents. That means that if this is true, then A must be 1 or 0. And then last one, Kaplansky unit conjecture, that this guy does not contain any non-trivial units. Means if A be equal to 1 in our group algebra, then A must have this form, where K is the scalar or element of a field, G is G. And there is this connection between this conjecture. If you like, you can find more interesting, some advances, some results in some book I will show you later. I will give a link. Okay, and in this February this year, this guy, wait a moment, it was a very big event. Where is here? This guy, he proved this conjecture. Wait a moment. This idempotent conjecture. Oh, sorry, unit conjecture. In here in archive, in this February, they told that if we have a torsion-free group, this group is a torsion-free, where, as usual, UV means acting, yes, acts, and we set X, Y, and Z equal to these guys. So, using this, then this guy is a non-trivial unit in group rings Z2. So we have to consider a field of a characteristic 2. So this is a very big result, and this guy is it's really a very big result. It's really a very big result. It's a very big progress in this way. So you see, unit conjecture now is false. Okay. This is a link. You can see it. Okay. So it was a historical background and some progress. And now, what about the homological and homotopical way, how to attack this problem, zero Kaplansky conjecture? Well, so let us fix some notations. Of course, let G be a group, and we assume that it's generated by some x1 etc xn, but maybe infinite. This is no problem. And define relations, we will denote it by R1 etc Rm, and we will use this presentation, group presentation. Of course, in other words, we can say that we have a quotient, yes, our group can be considered as follows, where free is the corresponding free group with these bases, yes, with the same generators, and N is a normal closure. Okay, so this is just notations which we will frequently use in our talk. Let us recall some definitions from algebraic topology. This definition will be very important for us. The standard two-dimensional complex or cellular model of presentation G is a two-dimensional complex that has only one single, has a single zero-dimensional cell, one-dimensional cell for each generators, in our sense N, yes, and circles, and two-dimensional cells for each, sorry, this is 4 and forget about R, for each relator Rj. In other words, we have one single point, one-dimensional, zero-dimensional cell. We have circles attached by this point to each other, and then we attach to any circle these guys, disks. Yes. Examples. Wait a moment. So this is a dense hat. Dense hat can be, you see, look at this. We have a triangle. Yes, first of all, I have to say, what does it mean? Sorry. Sorry. Examples, yes. Assume, let us consider this group G. This is, of course, trivial group, right? Generated by only one element X, and we have only one relation. You see, this is a trivial group. However, let us consider the corresponding to standard two-dimensional complex Kg. This is denoted by Kg, and this is called dense hat. This is the picture. Wait a moment, please. Yes, we have a triangle. Now we have to attach all these vertices to each other, and then we have to attach all these edges also to each other. We will get something like this. So I don't know. I think it is not so easy to see, but just imagine this how to use. We attach now RQ to PR. You get the column. And then you attach this guy to this circle, and you will get something like this. You will get a contractible manifold, contractible space, and of course, homotopical groups will be zero. Well, okay. Another examples, if you consider this cyclic group order 2, then the corresponding two-dimensional complex will be homotopical equivalent to the projective plane, because we have only one circle and we have to attach a disk and say that rotated by using this relation, we have to use, of course, we have to make, of course, a projective plane. Okay, so another notations, we have an orientation, of course, of the cells in the one skeleton, and this orientation determines an isomorphism. No, this is very easy to see. This is easily follows from the definition. And the two cells corresponding to relators, yes, as I told you, attach along a basic loop. So we have an inclusion, and this inclusion induces surjective with a kernel N, which is exactly normal closure of these guys. In particular, we have a fundamental group, which is, of course, is isomorphic to the free group generated by these guys. And that means that now, if we consider second homotopic groups of our two-dimensional complex, these homotopical groups will be left the G model, because we have an usual action of fundamental group. Our fundamental group now is our free group F, and so and we use not free group, our group G. So this guy's P1 is, of course, our group G, and this is very important for us. And
I didn't understand how does the first homotopic group, the fundamental group, acts on the second homotopic group?
I'm sorry. I don't
Which
understand you.
action do you mean here?
Action fundamental group on these guys. Yes.
Which action? How does it act? Canonically, what does it mean canonical? No, canonically isomorphic. This is clear.
I understand.
How does it act?
No, it's the usual. If you have a topological space, yes. If you define the homotopical groups, and if you have a second homotopic group which is not zero, of course you have an action. This is action just by conjugacy. So you have what does it mean? Elements of this guy. This is a loops, right? And what does it elements of this guy? This is the spheres, right? Image of your spheres, two-dimensional spheres. And you have a sphere, you have a basic point, and you have some loop which is start in your basic point and ended. And this loop gives a corresponding action of your fundamental group.
I don't understand. How does it act? So it should send some class of the second fundamental group to another class of the second.
Exactly.
How does it act?
Okay, let element of this is denoted by some alpha, right? Element of this guy denoted by some, no, for example, A. Okay, and acting is follows alpha A, alpha minus alpha A, alpha minus 1, alpha in the power I minus 1.
How do you multiply?
No, just alpha I, just alpha A, of course.
Now, how do you multiply elements of first and second fundamental group or homotopic group?
No, you have, okay, if you have, okay, let us start from basic definitions. If you have a topological space with a basic point, right, and you define the homotopical groups. Homotopical groups actually does not depend of your choice of basic point, right? Because you have a corresponding isomorphism, because you can move your sphere or along some path. Is it okay?
No, I don't understand what you mean to.
There is a simple geometric explanation. You can take a two-sphere, then you can shape it like this, and you have a very thin strip here. Then you can move this strip around the loop, and you are obtaining a new sphere.
Yes.
That's the very clear geometric interpretation of what does it mean for fundamental group to act on higher homotopic groups.
Exactly.
Does somebody else understand it?
I can draw you a picture, perhaps.
Draw me a picture, please.
Yes, it will be better if, okay.
Just a second. Yeah, okay, so, oh, I'm sorry. So you have a two-sphere, right?
Mm-hmm.
Then you can shape it like this, right?
Mm-hmm.
Now you have a path.
Then you can continue this process and you have a loop here. Then you can just put this basis point here and move this strip along this loop. You obtain a new spheroid in your space. So the initial spheroid was just the map that mapped this point to this point without any twisting. And the new spheroid is the one with the strip along this loop.
New element of the second homotopy group and after this action will be a new map from two sphere to our space, right?
Yes.
So what is the new map from our sphere to our space?
So this part of the sphere collapses to this loop, and then the rest maps like this. So is it clear that it is that two sphere is the same space as a two sphere together with the segment?
Yes, we just attach in an interval.
I see. You just compress
and now,
somehow.
Yes, and now you have to loop your interval.
Mm-hmm. Okay, more or less.
Okay. So that means that this guy is very important, second homotopic group. This is not only a abelian group, this is a model. And I also say that this guy is a relations among relations in our group. Again, we have generators, we have relations, and relations among relations. This is exactly this guy. This is roughly speaking, of course. So this guy is very, very, very important. Okay, so it was some examples we considered. Another ingredient, this is the Fox derivatives. We have to define Fox derivatives for free group, but then instead of these guys, we have to consider images. Okay, so step by step. So assume we have a free group. Let F be a free group with identity E and generated by some x1 and xn. Then the Fox derivative with respect to some generator denoted by this. This is just a function from here to here, just a map from here to here, such that this is true. This is of course chronicle delta. Okay, and look at this, please. You see that it seems like Leibniz product rule, yes, but I don't forget. Don't think about this. I didn't forget to multiply to v because of this is remark. The term derivative seems more reasonable if we think of S as an acting on its group ring on the right by the trivial action. And now we will get the third equation. We will get this one. So this is this is a Leibniz product rule, but we will not use this one. This is just for some reasons. Okay, so this is a definition of Fox derivatives. Well, some examples. By using those properties, we can calculate everything. I mean, calculate any Fox derivative. You know, for example, if we recall that this guy must be 0, where E is identity, yes. So we will get this one, for example. For x squared, we will get this one. For this word, we will get this one. So this is a calculation. Yes, I have to say that actually, if you use this definition, this guy is called not only Fox derivatives, this is called left Fox derivatives. Of course, if you say that now U is act trivially from the left side, you will get right Fox derivatives. So, but we will use left Fox derivatives. Okay. Now, magic is coming. Let we have a G with this presentation. Consider now our ZG modulus, this guy and this guy. So this is free modulus with rank M corresponding to the set of relations, number of relations, and this rank N corresponding to the number of generators. We have for the following map, which is homomorphism. Yes, this is the model homomorphism. By setting T means, of course, transposition. This is like a vector, as a vector. I have to say that by using Fox derivatives, we will get something like Taylor series, and we have this formula. For any element of free group, we have this formula. Yes, okay, nice. What else? Assume now, again, we have a group presentation. And now consider the Jacobian. This is just an image in here because we defined Fox derivatives for free group, right? But now it is very easy for us to do that we have to consider this one as an image, the corresponding image in our group ring Z. So consider now this guy, and it allows us to define this very nice map.
Just a moment. What do you mean by the image of a matrix in the group algebra? Do you mean the determinant of this matrix?
No. I mean, what does it mean? This is element, yes, this is some polynomial in our group ring, yes? This guy is some polynomial in our group, in a group ring or free group, by definition, right? But now, yes, but now instead of F, we consider now a G. and you have to use the corresponding relations. So this is image, I mean.
But this image is not in the group algebra. It is in the matrix ring over group algebra.
No, I mean image of any guy, of this guy. Yes, in your group ring. We start from the corresponding group ring from here, for example, right? So we will get something like this. And assume now that in your group G, xy, for example, equal to 1. And instead of this, you have to write 2 plus x, something like this.
I don't understand. Image belongs to which set?
Yeah, image belongs to group algebra, group ring.
So how can the matrix belong to group ring? This is n by n matrix.
Yes, and entry and entries is some polynomials.
So it belongs to the set of matrices over group ring.
Yes. No, any element, yes, is an element of your group ring, right?
So is the image not in group ring, but in the, I don't know, in the space of matrices over group ring, right?
Wait. Do you understand
the Jacobian matrix?
Guy...
I just read what is written. The Jacobian matrix is the image in group ring. Matrix cannot be in group ring. Element of group rings,
you mean
they are
this?
not matrices.
Okay, yes, I'm sorry. Yes, this is not so clear. Yes. Sorry, forget about this, please. And think about this as a matrix of polynomials in your group rings, in your group ring. Is
okay, because
okay?
my first idea was that you would consider determinant of this matrix, but you don't.
No, this is my fault. This is not nice. Yes, it is not clear. So any element you have to consider as a corresponding polynomial in your group ring. So okay, and this guy allows us to define this again homomorphism of modulus by followings. So this is a usual multiplication of usual matrix multiplication. Okay, well, and it was a very big surprise in this year, 1950, where the master, this very famous guy in knot theory, that since, first of all, second homotopy model, yes, we know, can be viewed as the kernel of this map. So kernel of this map, this is exactly this guy. It was a very big surprise. Moreover, we get this is very nice exact sequence. This is, of course, our argumentation. It is the usual definition in a group ring algebra. We send any element of group to 1, and this is identity for any integer number. Well, this is exact sequence. This is sequence is exact. This is very nice idea. So what does it mean exact? This is composition. For example, D1 with P is 0. Yes, D0 with D1 0, and epsilon with D0 is also with 0, and so on. Okay, so this was the last ingredient to formulate Roman Mikhailov approach.
Sorry, I again don't understand. Let us consider this theorem, yes? The theorem allows you to compute this second homotopy group, right?
Theoretically, yes, but practically, no.
Yes. For some concrete group G, yes? But what are the values of M and N? They should be somehow prescribed.
Yes, sorry, again, N is our generators, M is our relations. Yes.
I see.
Sorry. I have to say this here because you see everywhere I use let. Here I forgot it. Yes, this is this model corresponding to our relators. This model corresponding to our generators. So this is kernel of this map, and as I told you before, this guy is a relations among relations. This is another step of understanding what does it mean of what's happened. Okay, so this was the last ingredient. Okay, and what is profit? Okay, take some beta from our guy P2. Assume now that this is guy P, this is the map, yes? Assume that this one equal to this one. So since this sequence is exact, composition of this guy with this guy must be 0. That means that we get this one. This is exactly definition of our D2. Assume now that for a fixed I, we fix some generator. Yes, we fix generator and consider all Fox derivatives for all all relations R. Assume now for a fixed I, it has a common, no, for instance, right divisor F. That means that the previous, this one, yes, the previous guy, we then have this is, and if this is not 0, that it follows that our group ring has 0 divisors. So this is the homotopical and homological approach. Problems, of course, this is still complicated because first of all, how to compute this one? How can we understand is it 0 or not 0? So this is special theory, picture theory, identity sequences.
Sorry, I didn't understand. So this is a way to prove that the ring algebra, group algebra, has 0 divisors, right?
No, and yes, you're right, but I think it's better to think about this as a method to construct groups with this property. Because you start from with some generators, of course, and you start with some relator, and then you can construct another relators with these properties, just saying that any Fox derivative, of course, by fixed generator, must have this property. So left divisor.
What is F?
F is some divisor. We assume now that for a fixed I, yes, your relation, any your relation, if you using Fox derivative, have a common common right multiply F. F and D, there are some polynomials in your group ring.
I see. Assume that they are not coprimes, that there is some common divisor, then we have such a relation and it gives 0 divisors.
If and only if, yes, you're perfectly right. But if and only if homotopical group second is not 0, otherwise you will get 0, just 0 equal to 0. Because this map, yes, you see, it follows from here. And if this guy is 0, then image, of course, is 0, and you will get 0 equal to 0.
Okay.
Examples. Yes.
I'd like to ask why the sum of bj times dj is non-zero. Why it is a non-zero divisor?
I'm sorry. Why what? Why this is 0?
The sum. Well, this is the product of a sum and f is 0.
Yes.
So to say
it
that
follows from here. It follows from here. If you see, you fix some I, and for any j, you see this is sum.
Yes, I understand,
G, right?
Why the whole sum is 0. But I don't understand if you remove f in this sum, why it is non-zero.
What does it mean remove? I don't understand you.
If
we assume.
Well, we want to find 0 divisors. So we want to find 2 elements which are non-trivial and their product is 0. So you take one of elements f and another element is b1 d1 plus b2 d2, etc. Right?
Okay.
So why is this element b1 d1 plus etc. is non-trivial? Why it is does not equal 0?
How? Wait a moment. Can you repeat it? I don't understand you. If we assume, what we assume?
Well, we want to find the 0 divisor. So you claim that f is 0 divisor.
No, not on f and this guy also. Yes, this is sum.
Yes.
Okay.
But by this you claim that this guy is not equal 0.
We assume it.
But where do we assume it? I didn't see it. Why is this?
Ah, you mean if this is not zero, why this is not zero?
This is not zero, okay, but why the combination of dj's is non-zero? The combination of d1, d2, etc.
Ah, combination of dj with by j, this one is not zero.
Yes.
Ah, now I understand you. Wait a moment. Actually, I don't know, but
if it is zero, then we don't have zero divisors.
yes, I understand you. No, yes, I think it is possible. I think it is possible. Yes, I think it is possible. We will get some trivial zero divisor, right?
But in any case, this is not a theorem. This is just approach, just an idea.
Exactly. And nobody used this idea, okay. Except of me, of course, and Roman Mikhailov. So thank you for this question. Yes, this is a very nice question, by the way. Okay, let me give some example which appeared in my preprint. This one. Consider this following group generated by X and some Y's. Well, and let us assume that all relators, you see, we will use some, in some sense, semi-group representation, something equal to something, not equal to one. And any of these guys can be presented as follows. You see, U and V, there are some elements which do not involve X and X minus one. So they are from include only Y's. Right? A W is any, not necessary. This is any word, and this is our X. So, group with this presentation has non-zero divisors if and only if this guy is, of course, is not zero. And the proof of this, the result is not so hard. You can see it. Okay, let me just say how I construct this example. I just used composition diamond lemma. I start with the assumption we have a group generated by some X, and I construct some R, some first relator. I not construct, I just assume we have some relator. And by using composition diamond lemma, I will use some conditions to construct another one. And by induction, I will get this one. But this example is actually easy. And you can get it not by only using composition diamond lemma, but this is just the first step in this way. Okay, and I also have some ideas how to construct much more complicated examples. But I did not publish it yet, and I don't want to present it because maybe there are some mistakes. Okay. So this is an example. This is some way. Yes, you're perfectly right. Maybe it will be zero. Yes, you're perfectly right. But what is my approach? How to do? We don't want to think that we have a group. Let us check it. Yes. No. We construct group step by step. We start with some relator R1. We assume that this is true, without trivial zero divisors. Then we construct another Rj, and so on. So this is my approach. And okay, I almost finished. Now if you have some question, if you have some questions, I want to finish my report. Yes, as I told, this guy is very important, right? How to calculate it? As I told you, there are some theorems, some ways how to calculate it, and one of them is identity sequences. Again, we're given a presentation, and identity sequences. This is as follows: we have, let's see, I be some words in a corresponding free group generated by the same generators. which are conjugate of elements of form, right? And we set for any I, Ci will be this guy. This is again our acting, yes? I mean, this means that Wi multiplied Ti, Wi minus 1 in this power. Well, and this sequence is called identity sequence. If we multiply it, these guys, we have to get trivial element. I mean, identity element in our free group. Well, for identity sequence, we can define its inverse, well, and conjugation. How to conjugate as follows. And there are some Pfeiffer operation for identity sequences. It's look like, you know, like Nielsen way for free groups, right? It looks like this. We have to replace each by any word and so on and so on. And very nice result is if now we consider the corresponding equivalent classes, I mean equivalent classes with respect to these Pfeiffer operators, we will get some group, and this group will be abelian, by the way. And this theorem belongs to, right? You can find it here in this, for example, nice paper, that second homotopic groups is exactly this guy. I mean, group of classes of identity sequences. So it is some hope how to do. It is some hope how to attack. This is a very big, great problem in group theory. There are another theory how to calculate these groups by using picture theory. Jim Howe, he developed this theory in 1980s years. Algebraic also have some ideas and results in his books. So we have some hope, and I think it will be interesting. I think it was interesting, and of course, thank you for your attention. And I'm sorry for some minor mistakes.
Sorry, but I didn't understand. What is the result of your preprint on archive?
Result is I give a method, some sketch of method, how to make these groups with this property, and this is the result, one of them.
So please, what is the result?
This is this group. Yes, I construct this. Huh?
Let me read. So let me take a group generated by one letter X and L letters Y. And there are some relations.
Of this kind.
R11 equal R12, where this R are of specific form, right?
Exactly.
Okay, then if
second homotopic group is not zero, that this has no zero divisor. But actually the result is the Fox derivatives of these guys have common divisors. You see, any derived by any for any I, you will get this one. You see, so for any I, you will get this guy and this guy. This is common divisor for any I.
But you don't have such groups, or I don't understand. What does it give? If there is such a group with such relations, then it has non-trivial. Then the group ring has non-trivial zero divisors. So you don't know whether there exists such group with non-trivial second homotopy group.
Exactly. This is result is only about Fox derivatives. This is for sure. But if this is group has this guy not zero, so this is non-trivial zero divisors. And of course, another question: what about torsion? I also don't know. Maybe this group has torsion. By the way, when I discussed it with Jim Howe in his letter, he told me that in some cases we will get some torsion for these specific relators, of course.
But did you try to do some computations with concrete relation of this form, with simplest relations of this form?
Yes, but yes, you're right. But again, it is just in some sense this is just the first steps. It is really very complicated, but I'm trying, because in some sense this example is very easy, is very simple. in some sense, of course. However, the method by using composition diamond lemma and so on, we can use, we can make another examples, much more interesting than this one. But again, this result is about common divisors of Fox derivatives only.
And so you put this observation, let me say, on archive, something like 3 years ago.
Something like this, yes.
And this is on archive and nothing else.
It was first version. Now it has, now maybe it is third version, because the first version of my paper was, no, okay, how to say, now it's much more interesting to read, I think, I hope, of course.
And you put it with a hope then somebody else will develop your ideas and get a counterexample to Kaplansky problem, or what was the aim to put this on archive?
What is the aim? Yes, aim, yes, maybe somebody, yes, maybe for somebody, yes. And when I uploaded, in next day, Jim Howe contacted with me and we discussed something. So Roman Mikhailov also was interested, because I did not invite, I didn't know him face by face. I mean, I didn't met him face by face, and after that we have some correspondence. We talked about this, and he invited me in his laboratory in St. Petersburg when I was in Prague.
I see. So this submission to archive leads to some profit, right? So there is some, there are some consequences.
Yes.
Are there any more questions, comments? If not, then many thanks to Viktor for his nice talk and presentation. And these are really beautiful problems. And it's very interesting to think about such clear and elementary things. And this is still open. I see.
Thank you for the attention. It was a very big pleasure for me. And again, I'm sorry for many mistakes.